In this video, I will use a very cool tool, which is called Playground Tensor Flow. I will add the address to it in a link to this video in the comments. And this is a tool which allows experimentation with basically neural networks on a couple of predefined data sets. So first I just want to give you a quick tour of the user interface. Over to the left here, we can select between 4 different data sets. So this is just data points basically, which is defined on x1 and x2 as the inputs. So we have 2 inputs, x1, x2. And there are 4 different sets of data. And from these data sets, we can then construct features which forms the input to the neural network. So this is the neural network part. This is the feature definitions. So we can choose to feed the neural network either simply with the x1 and x2 variables themselves. We can alternatively select to feed the neural network with x1 squared or x2 squared. Notice that the way this GUI works is that negative numbers are plotted in orange and positive numbers are in blue. So here you see x1 is orange to the left where it's negative and blue to the right. x2 is orange in the lower part where it's negative and positive in the upper part where it's blue. The square of x1 is of course always blue unless it's near 0, then it's white. And the same thing for x2, it's also always positive or near 0. Another possibility is to use the feature which is x1 times x2, which looks like this checker pattern here. Or we can use sine of x1 or sine of x2. So that's a total of 1, 2, 3, 4, 5, 6, 7 possible features which we can supply to the neural network. Furthermore, we can then select how many layers we want in our neural network, and for each layer we can select how many neurons we want for each network. For those of you who are not yet familiar with neural networks, I will later upload some videos which goes through theory behind neural networks and deep learning in details, but those are not available yet. So for the purpose here, the main thing I want to show is the practical aspects that I have discussed in these introduction videos. And try to use this tool to give you some understanding on these concepts. So the first thing we can do is to select a data set which is actually very simple to model, because we have one set of data over here and one set of data over here. And since this is very simple to model, we can just start with selecting the variables themselves, x1 and x2. And I think you can already sort of see that combining x1 and x2, it's very easy to draw a line here and say that this is the orange dots and this is the blue dots. And since it's a very simple problem, we can get away with probably just one hidden layer and one neuron, and then we can try and train that. Let's see, we do it here. Yeah, and indeed the system easily finds this combination of x1 and x2, which gives us a separation between these data points. So straightforward, and it's very fast. It trains to this level immediately. We could also, if we wanted to, play with the activation functions here. We could use, for example, rectified linear unit. Run that again, same effect. With this simple problem, it doesn't matter too much. But of course, this is a very simple set of data where the data is already separated. If we were to choose something a bit more complicated like this, and now try to train using the same network structure, we see that this network fails miserably. It's not able to find a model which can explain this data, where the blue dots are in the middle and the orange dots are located around like this. So we can try to, for example, increase number of neurons here, like this. Let's say just try 4. We see that with these 4 neurons, we are able to describe something like a square, which then sort of manages to model the data. If we maybe try with 3, still sort of a square. It's not a very accurate model of the data, but it's sort of acceptable. But it shows that because we have a slightly more complex problem, we'll need a slightly more complex model. This we talked about in the introduction videos, that one of the things which makes machine learning work is the ability to describe complex relationships in data, this description power concept. And we see here that how much description power we need depends on how difficult problem we are working on. For this simple set of data, it's no problem with 1 neuron to learn the relationship. In fact, if we add a lot of neurons, see if we can have some kind of overfitting maybe. We see that the model by random chance thinks there is some structure up here, which is not really true. It's just a noise in the model. So if we return to this case, try to run that. Now we have a bunch of hidden neurons in the hidden layer, so it starts to resemble a more or less acceptable model. We could try to add another layer, see if that will help the modeling a bit. See, yeah, it's still more or less acceptable. You can go to, I think, what is the maximum size here. We get now a pretty good model. Now if we think a bit about what we actually have here, we see that there is sort of a circular pattern here to this data. So one of the things which I tried to explain in the introduction to machine learning videos was the importance of understanding the problem we are working on. So by realizing that this dataset here is actually circular, it makes much more sense to use these features, x1 times x2, x1 squared and x2 squared. And now if we try to train the network, you see that we immediately obtain this circular model here. Probably we don't even need this neuron. Yeah. So just from 1 neuron, we are again able to explain the data by using some knowledge of the data in the feature selection, what we put into the neural network. And this shows this very important principle that machine learning really isn't as simple as just stacking up an algorithm and putting some neurons in a hidden layer and pressing play and hoping for the best. If you just do that, we see we end up with something here which either doesn't work or which is much more complex and therefore slower than it really needs to be. See here, it takes a while to train, and the performance is still not as good as what we could achieve by using some insight into the problem itself. See here, we get good training performance much faster. One further such case is this. Here we have this data which is separated into quarters. If we now try to do that with the x1 square and x2 square features, you see that this is sort of based on the assumption of some circular patterns in the data. This is very much not circular, so we don't get anything useful out of that. We can try to add more model complexity. Still doesn't really provide any useful model here, because this is basically always trying to find something which is circular. So if we add in these features, we see that we are trying now to obtain something which is 2 circles. And try to remove this. Yeah, then we get a model which is more or less feasible. Maybe we can reduce the model complexity. Looks like we are still able to achieve our model. Can we do it with one hidden layer? Looks like we can, but it's slower. So you see the importance here of having some intuition behind how we select the model, how many layers, hidden layers, how many neurons. That is the model complexity. And also what input we put in, the features we select, and how all of this relates to the data set or the problem that we are investigating. Of course, the easiest thing to do here would be to use this, which is x1 times x2. Then it's going to work fine with a single neuron again, because we now select the features using understanding of the problem, and then we can get away with a much simpler model. So I think this little demonstration shows a couple of very important things. Number one, that selecting neurons and hidden layers, or in general these hyperparameters of the neural network, which we will get back to later, is not really straightforward. It's some trial and error involved, and the best way to succeed in doing machine learning is to remember these engineering principles, that we really try to use our understanding of the problem. And finally, I would just encourage those of you who are trying to learn to be good at machine learning to play with this tool, playground.tensorflow.org, and then just start to develop some sense of what all of these hyperparameters does, how feature selection affects the outcome, and the complexity of the model required in order to achieve results. Try to get some understanding of how machine learning works in practice. This tool is a very useful tool towards that goal.